How can we find out the number of stereoisomers in a particular organic compound? So, number of stereoisomers. Number of stereoisomers can be found out by using a formula that is 2 raised to n, where n is the number of stereogenic centers. So, if n is the number of chiral centers or stereogenic centers, then the total number of stereoisomers will be equal to 2 raised to n. For example, glyceraldehyde. Glyceraldehyde is CHO, COH, H, CH2OH. And we know there is only one stereogenic center. So n equal to 1 and the number of stereoisomers equal to 2 raised to n, that is equal to 2 raised to 1 equal to 2. So glyceraldehyde has 2 stereoisomers. If we check this compound, we can easily say that one of the stereoisomer will be the mirror image of this compound. So that is the next stereoisomer of glyceraldehyde is COH, H and CH2OH. And these two structures are mirror images. So these are enantiomers. And we know that these enantiomers are optically active. So both the stereoisomers of glyceraldehyde are optically active compounds. The next one is lactic acid. We know lactic acid is COOH, COH, H, CH3. Same as that of glyceraldehyde, this compound also contains only one stereogenic center, that is n equal to 1, and hence 2 raised to n equal to 2 raised to 1 equal to 2. So 2 stereoisomers are there, and the next one is the mirror image of the first one. And hence these two are related as enantiomers, since these are non-superimposable mirror images. And there is no question about optical activity. It is optically active. Then tartaric acid. Tartaric acid is 2 COOH groups are there, and two stereogenic centers are there. These two centers are attached to OH and the hydrogen. So I'm going to write the structure of tartaric acid like this. So here number of stereogenic centers are 2, that is n equal to 2. So total number of stereoisomers are equal to 2 raised to n, that is 2 raised to 2 equal to 4. Number of stereoisomers are equal to 4. Now let us draw the stereoisomers of this compound. One of the isomer is this. The next one will be the mirror image of this, that is COOH, COH on left side and the hydrogen on right side, and the hydrogen OH. This will be the mirror image of this compound. This is the second stereoisomer. And these two structures are related as enantiomers. These two are enantiomers. What will be the next stereoisomer? The next stereoisomer will have two OH groups on same side. So the structure will be like this: COOH, C, C, COOH, OH on right side. Here also OH is on right side and hydrogen is on left side. Here also hydrogen is on left side. So next, to draw the fourth stereoisomer, we have to draw the mirror image of this compound. Is the COOH. So we'll think these two are two isomers and these two are related as enantiomers. But that is not true. These two structures are not related as enantiomers, because if we clearly look these structures, we can see a plane which is passing through this bond will cut the molecule into two identical halves. Same way in this molecule also, the plane passing through this bond cut this molecule into two identical halves. That is, these molecules possess a plane of symmetry. If there is a plane of symmetry, we cannot say these two are enantiomers, right? These two structures are expressed in two different ways, but actually these two are same. That is, these two are identical structures represented in two different ways. So this is actually a single structure. So theoretically there are 4 stereoisomers, but in actual case there is only 3 isomers. This is the 1, this is 2, and this is 3. 3 and 4 are identical, so these two are considered as only one stereoisomer. In actual case, only 3 stereoisomers are there. Then coming to the optical activity of these compounds, the structures 1 and 2 are optically active. But coming to 3 or 3 and 4 structures, these are optically inactive. Optically inactive structures. The reason behind this is, here the plane passing through the center of this molecule cut the molecule into two identical halves. And if plane polarized light is passing through this molecule, one of the half rotate the plane polarized light in clockwise direction and the next half rotate it in opposite direction. So the resulting optical rotation will be equal to 0. So the resultant specific rotation is equal to 0, and it is considered as an optically inactive compound, and this process of internal cancellation of the specific rotation is known as internal compensation. So this process is known as internal compensation. And this compound is known as Meso Compound. Meso Compound. Then, coming to the relation of these compounds, we already told that 1 and 2 are related as enantiomers. 1 and 3 or 4 are diastereoisomers. Diastereoisomers. Same way, 2 and 3 or 4 are also diastereoisomers. Here we learn a new word, that is meso compound. Meso compound means compound which contain 2 or more chiral centers but optically inactive due to the presence of plane of symmetry. Here the example is tartaric acid. This is the meso-tartaric acid. And the reason behind the optical inactivity of meso compounds are internal compensation. Now we have to familiarize one more word along with meso compound, that is racemic mixture. Like meso compound, racemic mixture is also optically inactive. In meso compounds, optical inactivity is due to internal compensation, but here optical inactivity is due to external compensation. Before that, we have to know what is racemic mixture. Then only we can understand what is external compensation. Actually, racemic mixture means a mixture containing equimolar enantiomers. It's a mixture of equimolar enantiomers are called racemic mixture. For example, racemic mixture of lactic acid means this mixture containing plus and minus lactic acid. That is, this mixture contain both plus lactic acid and minus lactic acid. So, racemic mixtures are usually denoted as plus minus. If it is a racemic mixture of lactic acid, then it is represented as plus minus lactic acid. Or we can also use the symbol DL. DL, lactic acid, is also representing the racemic mixture of lactic acid. Now we can explain external compensation. So that is, here in this mixture, we know equimolar of plus and minus lactic acids are there. So if plus lactic acid rotate the plane polarized light in clockwise direction, the minus lactic acid rotate the plane polarized in anti-clockwise direction. So what happens? The net rotation of this mixture is cancelled. So the specific rotation of this mixture will be equal to 0. And the process is known as external compensation. Racemic mixtures are optically inactive due to external compensation. But unlike meso compounds, optical inactivity of racemic mixture is only temporary. That is, we can make this racemic mixture active by separating the enantiomers from the racemic mixture. So separation of enantiomers makes the mixture optically active, and the process of separation of enantiomers from racemic mixture is known as resolution. So resolution of racemic mixtures make them optically active. Coming to meso compounds, the optical inactivity of meso compounds are permanent due to the presence of planar symmetry. Then the process of preparation or the process of conversion of an optically active compound into a racemic mixture is known as racemisation. So racemisation is the process of conversion of an optically active compound into a racemic mixture. That is, if we have a pure D form, we can convert this into a mixture of DL by racemization process. Racemization can be done by using many simple processes. For example, racemization can be done by heating an optically active compound or treating the optically active compound with a suitable reagent, or sometimes auto-racemization is also occurs. So first one, by heating. This is normally occur in lactic acid. Tartaric acid is also an example. So when a D or L form of lactic acid or tartaric acid is heated, it is converted to its racemic mixture. That is, if we heat, it will convert into its racemic mixture. And the second process is by treating with the suitable reagents. For example, mantelic acid converts to its racemic mixture when it treats with hydrogen bromide. Then the third process is auto-racemization. Auto-racemization means racemization occurs in some optically active compounds when it's keeping for a long time. For example, dimethyl bromosuccinic acid if we keep dimethyl bromosuccinic acid for a long time, the optically active compound itself converts to a racemic mixture. So that is auto-racemization. So these are the methods which is used for racemization.